In this video, we are going to begin our discussion of limits of vectored value functions. I'm not going to go through the complete theory of how it works. I'm just going to give you the definition. It's very easy to see. I would recommend you taking the definition of a limit and running it through a vector, and you can see how nicely it works out. So what happens here, and I'm going to write this definition out, is if I have r of t, and I went ahead and defined it up there as x of t, y of t, z of t to help me write this out. So if I want the limit of my vectored value function, all I have to do is take the limit of each part. It's nice and easy. Limits aren't going to be as nice later in 3 dimensions. So let's enjoy it while we have it. You may have forgotten a few of your techniques. I'm going to try to hit a few different ones here to help you. All right, so what I just wrote out, what this means is that if I want the limit of a vectored value function, I just find the limit of each component. That's all it is. It's going to be nice when we go forward with calculus. A lot of this is going to apply in that same way. It extends to 3 dimensions by doing it 3 times. So what I like to do, and I recommend this for points, for me, on my assessments, quizzes, whatever I give you, is do each part by itself first. This is going to keep you from doing any silly notational mistakes. There we go. So remember a limit, if I can plug it in, that's what I do. So this limit is equal to the square root of 2. That's the first one. All right, then I'm going to work the second one. Limit as t goes to 2 of 4t squared over t minus 2. I'm going to leave that blank for a minute. I don't know if you guys can see it. I can factor out a 4. And then this actually factors to t plus 2 times t minus 2. The reason I'm doing this is if I try to plug in, we always just try to plug it in first. But if I plug it in here in the denominator, if I put a 2 there, I got 2 minus 2, and I'm dividing by 0, which I can't do. Now, one thing I want to voice, because I always get this on my test, just because you can't plug it in doesn't mean the limit doesn't exist. I have so many people just plug in 2, and they're like, oh, I can't divide by 0. D and E does not exist. Limit doesn't exist. Well, that's not true. We can manipulate things algebraically to help us find an answer because we don't care what happens at the point. We care about what's happening as we approach it. What is it going to? So I'm going to replace this. T plus 2, t minus 2. All right, this is equal to, now I can cancel the limit as t approaches 2 of, okay, well, actually, t minus 2 goes away, so it's just 4 times t plus 2. And we can literally just plug 2 in, which is going to get me 16. One thing I do want to point out, and I will count off, it's time to get this down. In Calc 1, when I'm teaching Calc 1, I'm a little more graceful, but you keep the limit until you plug it in. Please do not drop it. I will be picky with notation with this because you've had 2 classes to get that down. Now, am I going to destroy you point-wise? Definitely not. I'm not that kind of grader. But you do need to be careful because I don't know who you're going to get next. I've had professors that will, the first thing, I had this one guy and it was like proof. So we'd write sentences and paragraphs. But the first thing that he would read that was wrong, he'd count it off and quit grading. And the rest of it would be, I'm sorry, you messed up at the beginning, so I'm not even going to look at the rest. I will not do that. I will look at everything. But it's time to get your notation close to flawless because you are about to go into heavy application after my course. After you get past your sophomore year, wherever you're at in your journey, once you get to the applications, notation is going to matter. So please communicate mathematics correctly to build yourself a successful career. Okay, I'll get off the notation high horse. I guess it's a platform, not a high horse. I'm not. Anyways, okay, I'm going to quit talking. The limit about other math, not math stuff. Let's do the z component. First thing we check, can we plug it in? And the answer here is yes. Okay, so I got a 2 on top and a 6 on bottom, which is a 1/3. Now, what you just did is not answering the question. The question wants, what is it going to? Well, in vector value functions, we describe points as vectors. So the first component is square root of 2, the second component is 16, and the third component is 1/3. There is my answer. So do each component separately. The reason I'm doing that is because I don't want you to mess up your notation, and everybody messes it up. So please just be very careful. Do each limit by itself, and then just write down your answer in 3 parts. Do not do the limit in all 3 parts. I promise you, you're going to mess up the notation. If you can prove me wrong, please do. Okay, so this next limit, these are a couple of tricky trig ones that I know you all love. So let's break this one down. The limit as t approaches 0, that positive means we're just coming from positive numbers. The reason that that's there is right here. ln, we can't take negative numbers. We can only think about positive numbers. So the first thing we're going to do is just the cosine. If we can plug it in, we plug it in. Gets me a 0. That's a good answer. All right, so we'll leave that. All right, our next one is tangent of t over t. So notice that this, if I plug in 0, it goes to something called an indeterminate form, meaning tangent of 0. You can plug that in your calculator, 0, and then plug in t. I get 0 over 0. Anytime I get 0 over 0, so let's write this rule because everybody uses it wrong. Hospital. L'Hôpital, I think that's how my professors pronounce it. So that's how I will do that. You can correct me if you'd like in an email if you know how to pronounce it. That would be great. I'd love to say it right. Anyways, so if we get 0 over 0 or infinity over infinity, we can use that rule by taking derivative of top and bottom. Taking top and bottom. The reason the reason I'm giving this, that's my train of thought, is that students, as soon as when I teach Calc 1 and students first learn about this rule, they get really trigger happy about using it. They want to use it all the time because it is a very nice, nifty rule that will keep us, like we could have used it above if we would have got a 0 on top, which we didn't. But we could have. Actually, I'm kind of curious. Does it? Yeah, it does. 0. We could use L'Hôpital's rule right here, right? And not done any factoring. So you just have to be very careful. We do get 0 over 0. So what that means is I always signify to my grader what I did because it's kind of hard to pick up. You can do that in any way. I always did do that. That's what my professor showed me back when I was in your shoes. And then what we do is we just take the derivative of the top and bottom. Derivative of tangent is secant squared. The derivative of t is 1. And now we can actually do that because I'm not going to divide by 0. So we got secant squared of 0. Secant squared of 0, well, that's kind of hard to understand, right? Depends on how good you are at trig. I think about this instead. I don't have my secants memorized, but I have my cosine memorized. I know that cosine of 0 is 1, so 1 over 1 is 1. So you can use L'Hôpital's rule. Just be very careful that it does meet this requirement. I have so many students just like trigger happy, use it all the time, but you have to get one of those. All right, I'm going to show you some manipulation here, a trick. Upper math really is about just manipulating what you want. So I have this t times ln of k. Sorry, k, I don't know where that came from. T, oh, the k came from here. All right, if I plug in 0, I can't do it. ln of 0 does not work. We can't do that, so we have a domain issue. So instead, what I'm going to do is I'm going to force a L'Hôpital's rule to happen. So I'm going to put my limit there. I'm going to rewrite it so I don't miss points. And then here's the trick. I'm going to do ln of t, 1 over t. Okay. Now, as soon as now if I do this, think about ln, that function looks like this. So as 0, we get close to 0, this goes to negative infinity. This, as it goes to 0, goes to positive infinity. And really, we could do a plus or minus there. So since both we have infinity over infinity, this tells me that I can use L'Hôpital's. So I'm going to do that. So here's my indicator to my reader that I am going to use L'Hopital's. So ln is 1 over t, and then the derivative of 1 over t is negative 1 over t squared. If I flip that over, right, that is just that algebra, 1 over t times t squared over 1 with a negative. We get negative, so I'm going to rewrite my limit real quick. Limit t as we approach 0. And then if I'm looking here, it just ends up with a negative t, which means I can plug a 0 in. So this limit, here we'll do this. Limit, we'll be lazy here. As t approaches 0 of r of t is equal to each component 0, 1, 0. So the limit is approaching that point, the function is. All right, so limits, it's just, it's the same as Calc 1, it's just probably been a while, and then if you guys are like me, when I first hit limits in Calc 1, it was pretty confusing, like, to get used to that kind of thinking, because it's much different than algebra. So you may need to review your limits, just use the same book that we're working out of, and go back to the section about limits, and if you want a solution manual, you just need to reach out to me. I can give you some problems or some solutions to some of the problems out of the book if you need to review limits.